So, up until now, you have been told benzene does not get broken. We don't touch benzene. We don't do anything with benzene. The carbons in benzene are not nucleophiles. They're not electrophiles. They like to stay as they are. And now, we've got to the point in organic chemistry where we can touch benzene. I know, lots of fun. And so, today we're going to learn one of the mechanisms by which we can substitute one of the hydrogens on benzene for something else. And so this is called electrophilic aromatic substitution. And it's got components of reactions that we've seen before. The beginning looks a lot like addition, and the end looks a lot like elimination. So this is basically a partial addition and a partial elimination. And later, actually, we can learn about nucleophilic aromatic substitution. I can make a video on that, and that is actually elimination addition, sorry. So that's backwards, elimination addition, then this, which is going to be addition and then elimination. So that probably all sounded very confusing. It's going to make more sense once I draw this out. So each of these carbons has got one hydrogen on it and 3 bonds to other carbons. And we said this is electrophilic aromatic substitution, so we need an electrophile. And I'm going to put this as E generically, and it's usually positive. But I know it can be confusing to just use a random letter, and I like concrete things and knowing, okay, this can happen with this and that and that. But the reason why I'm using E, the way people kind of use R for a carbon group or X for a halogen, E is our electrophile, is because a lot of these electrophiles have to be such strong electrophiles that we need like an extra step to create them, and that complicates things. So we're not going to do that. But I told you this looks in the beginning like addition. So what's going to happen is, yep, you guessed it, the double bond, or one of the double bonds in the benzene is going to act like a nucleophile, and it's going to come and grab our electrophile. And so what this is going to do is it's going to do exactly what we did in addition, where we had the cation and Markovnikov's rule and all that fun stuff. We are going to make a cation. So one of the carbons in that bond is going to make a bond to the electrophile, and the other one is going to make a cation. And in this case, it doesn't matter which, because our benzene is very symmetrical. So let's randomly say that this is going to be a cation, and this one is now going to be bound to our electrophile. And this cation is actually really stable because of resonance. So what we can do is we can take this bond here, and it has to be this one because the other one's too far away. It's not conjugated. And we can make a resonance structure where that bond travels over here, and now this one is positive. I hate these substitutions a little bit because you have to draw all the hydrogens for it to kind of make sense. And then we still have this bond here. And so essentially what we can do at this point is draw a whole lot of resonance structures and do what my old British chemistry professor called chasing the copper cation around the ring. So actually I'm going to do us a favor, and I'm going to pause this recording and draw them all out and then come back. Okay, well, I miscalculated. Turns out there's only really this one. There's only one more, but it's still a lot of drawing. But now we switch gears, and we're not going to be doing an addition type mechanism anymore. We're going to be doing an elimination type mechanism. So this last step is going to look a lot like E1. And so remember, in E1, in both our elimination reactions, we had a base. And this base is going to take a proton, because that's what bases do. And it's going to take the proton that's on the same carbon as the electrophile. And that's convenient for us because we want to substitute, so we have to get rid of something. And hydrogen's not a very good leaving group, so we're not going to kick it out like a leaving group. We're going to take it like a proton. And whenever we take a proton, the electron pair has to go someplace. And in these elimination type mechanisms, the electron pair goes and makes a double bond. And we can do this in this resonance structure where I'm doing it. We also could have done it in this one. We could have taken this proton and used that electron pair and made a bond here. But it doesn't matter. So This is going to now get us, so we're not going to be in the resonance structures anymore. This is going to get us our product. And now instead of a hydrogen on that carbon, we have an electrophile. And so oftentimes what's actually going to happen is that in the process of making our electrophile, we're going to use a catalyst, and that catalyst is going to get electrons because it's going to be leaving the electrophile deficient, and then that catalyst, the changed version of the catalyst, can act like a base, and when it takes the hydrogen, somehow it'll revert back to the original catalytic form. So that's electrophilic aromatic substitution, the mechanism. Now we can go over some of the specific things that we use in electrophilic aromatic substitution. So one thing we can do is halogenate our benzene, so halogenation. This we can do with iodine, with bromine, with chlorine, not with fluorine. Fluorine is awful at organic chemistry. I probably say this a lot whenever I talk about halogens, but it is, don't use it, etc. But with halogenation, we're going to be using like the dihalogen version. So for example, if we're brominating, we're going to use Br2. And we're going to need a way to make this electrophilic, because right now it's not very electrophilic. So we're going to use a catalyst, and it's called iron tribromide. And if we were using chlorine, it would be iron trichloride. If we were using iodine, it would be iron triiodide. But what iron tribromide is going to do is this bond. One of the bromines is going to pack up this bond and go and attack iron, which is a metal, and so it's electron deficient. And this is going to get us a bromine cation and FeBr4. So this is our electrophile, this bromine. And then FeBr3 was a catalyst, and so we need to get back our catalyst. And like I said, sometimes the way we do this is at the end when we have our benzene that is all ready to transform itself. So the bromine will be here. We'll have a hydrogen here, here. The benzene is all ready to become its new substituted form. What we're going to do is an E1 type reaction where one of these bromines is going to take its electrons and attack a hydrogen, and the electron pair from the hydrogen is going to make the double bond. And in this way we're going to get HBr as a side product, and then FeBr3 will be returned and we'll have our catalyst again. Another thing that we can do is nitration. In nitration, we're going to be releasing water. So we're going to start with nitric acid. And it's got more resonance forms than this, but this is the one we're going to focus on. And we need a catalyst, just like last time. And the catalyst is going to be sulfuric acid, which I'm going to draw like this, even though you see it H2SO4. This is same atoms, different order. And we're going to have this oxygen is going to take a proton, and these electrons are going to go to the oxygen. Now, why the heck are we not taking this hydrogen with the negatively charged oxygen? Well, the reason why is we're trying to make a nice leaving group here. We're going to make a water leaving group, and it's going to get out of there. And we need our O- because how do we typically kick out a water leaving group in like carboxylic acid or whatever other reactions with carbonyl compounds? How did we do that? We would make a double bond with an oxygen. So we get this, and one of these H's is from sulfuric acid. And here is our nitric acid with our extra hydrogen. We're going to kick a pair of electrons into here, and we're going to make water leave. Now there's a very handy concept called conservation of charge, and it goes like this. if you start with a charge at the beginning of your reaction and you have the same stuff until the end, then you need to end with the same charge, or things need to add up to the same charge. So if you add up plus and minus, that is plus. And if you kick out water, and water is going to be neutral, so here, that's a bad error. Here was neutral water going out. We need to have something positive remaining. And this positive thing is called the nitronium ion, and this is going to be our electrophile. And so what's eventually going to get made here is called nitrobenzene. And you're going to be hearing a lot more about nitro groups, but they're very electron withdrawing, and that's going to be good for some reactions of benzene and bad for some other ones. And then we always need a base in these reactions, and once again our base is going to be just regenerating our catalyst. So we have HSO3 minus is our base, or HSO4 minus is our base, and it's going to take back a proton, and it's going to become sulfuric acid once again. Another reaction we can do is called sulfonation. In sulfonation, you are adding this thing to benzene. So this SO3 is a good electrophile all by itself. It doesn't need any prompting from a catalyst. We do have a catalyst, though, that comes in later on, and that's sulfuric acid. And sulfuric acid is always going to be in equilibrium with its conjugate base, which is HSO4 minus. And so we're actually, in this case, going to use HSO4 minus first. But we write H2SO4 just because it's easier that way, and because, like, that's how it probably comes commercially. Like, we don't get a bottle of HSO4 minus. Anyways, so this HSO4 minus is going to take a proton from this kind of finalized form, or like the almost final form. And at this point, the SO3 is actually going to look like this, because we had the benzene attack it, and then we needed to have some type of leaving group, and that was one of the bonds and one of the oxygens. But this HSO4 minus is just going to take a proton, and this is going to finish off the reaction like that. And then I'm not going to draw these hydrogens anymore. I'm just going to draw the benzene with our SO3. But then this SO3 is actually going to take back a proton from this sulfuric acid, and that's going to leave it as HSO4 minus again. So it is a normal catalyst because it gets regenerated. It's just kind of backwards because we don't start the reaction with H2SO4, we start it with HSO4 minus. And now we get to a fun pair of reactions. They were made by two people called Friedel and Crafts. So Friedel, Crafts. And they can be kind of confusing because they did an alkylation and they did an acylation. But luckily for us, both of them are pretty similar. So we're going to start with the Friedel-Crafts alkylation. And in the Friedel-Crafts alkylation, you have to start with a halide form of your group that you want to add. So let's say that I want to add isopropyl. Then I'm going to have isopropyl chloride. And so what's going to happen is we have an aluminum trichloride catalyst. And you might remember aluminum trichloride from when we were learning about Lewis acids and Lewis bases, and AlCl3 was a Lewis acid because it liked electrons. So that's just another word for electrophile. So we're going to have our catalyst be an electrophile, and then after that we're going to make a carbocation, which is going to be our real electrophile that benzene attacks. So kind of like how we did in the halogenation, the chlorine's going to pack up its electrons and go over to aluminum and live there for a while. And we're going to have an isopropyl cation and AlCl4. And so benzene will attack the isopropyl cation, or whatever cation that you want to make. And so for Friedel-Crafts alkylation, you have to remember that if you don't have a good cation, it's either going to take longer or maybe it's not going to work. And then at the end, when we're almost done with our reaction, we have this thing, which we're starting to get very familiar with now. That's supposed to be a double bond, not a triple bond, but I don't think I drew it well the first time, so then I drew it again. But we have now our isopropyl on there. And one of these chlorines from AlCl4, so I should draw it again. I should have drawn it like this. One of these chlorines is going to pack up its electrons and grab the proton that we want to get rid of and leave the electrons on the benzene ring. And in this way, we're going to get our product and regenerate our catalyst. There's one problem that I need to address with Friedel-Crafts alkylation, and that is that sometimes there are groups that you just can't add through Friedel-Crafts alkylation because of rearrangement. So for example, let's say that I wanted to add not isopropyl but N-propyl. So I could start with N-propyl chloride, and we know this isn't going to turn out well, but we're going to try it anyway. And the chlorine is going to go join aluminum, and we're going to get this cation. And what do we notice about this cation? It's primary, right? But we know, because we just used isopropyl, that we can make a better cation because right next door are two hydrogens, and these two hydrogens, one of them can go and take its electrons with it and go over to the other carbon, and we do a little hydride shift and get an isopropyl cation. And then if we do this reaction, we're going to get isopropyl benzene again, and not N-propyl benzene. And there is a solution to this, and we're going to come back to that in a second. And if you want to try to get ahead of this, if you're bored because I'm going too slow in this video, you can try to think about what that solution might be as we learn the Friedel-Crafts A solution. You're going to need the Friedel-Crafts A solution to solve that problem. So an acyl group is anything that has a carbonyl, and actually I want to make it 3 carbons, a carbonyl and something else. And in this case, the something else is a chlorine. So we're starting with an acid chloride, and we're going to have AlCl3 again. Luckily for us, these are kind of similar reactions, and this chlorine is going to go to aluminum, and we're going to get this cation. And so whenever I've seen cations with oxygen right next to it, on the same carbon, I used to get confused because I would think oxygen is electronegative. Why the heck does this cation want to stay with an electron withdrawing group right on the same carbon? That's awful. Why doesn't it rearrange? And so it turns out there's a super weird resonance structure on this acylium cation. That's what it's called, by the way, acylium. And I had to go and look this up because I totally forgot about it. But this oxygen, which has 2 electron pairs right now, 2 electron pairs, that's right, is going to kick another electron pair into that bond, and we're going to have this. And I know that's not the geometry of a triple bond, but now the oxygen is positive, and we have a resonance structure. And remember that resonance beats inductive effects, so even though inductively the oxygen is withdrawing electrons through a dipole, it's also giving them through resonance, and resonance is more powerful, so therefore this thing is pretty stable, and this cation is not going to want to rearrange. So that's useful for us, because now we can take benzene, and benzene can attack the cation. And so eventually we're going to get this, and I'm not going to do the regeneration of the catalyst this time because we did it already with aluminum trichloride, but we're going to get this 3-carbon acyl group. And this is how we solve the problem of how do we put on alkyl groups onto here that we can't do through Friedel-Crafts alkylation because they can rearrange. Well, we use the Friedel-Crafts acylation, and then we're going to do a reduction. So this thing I'm about to show you is called the Clemmensen reduction. And we take zinc and mercury and aqueous HCl. Don't ask me how this works. I don't know. You don't have to know. And so here is what we get in the end, and that's how we can put on all kinds of carbon groups onto a benzene. There is one problem with the Friedel-Crafts acylation, one limitation, and that's that the formyl cation, which is if you start with formaldehyde or like formyl chloride or what the heck you call it, and you go through AlCl3, this thing, even though I guess it also has resonance, is so unstable that it doesn't happen. And so you have to kind of go in a roundabout way. And so what we're going to do is something called the Gattermann-Koch formulation. And in this guy, we have carbon monoxide and HCl. Don't try this at home. And we're going to get the formyl cation in this way. And apparently somehow this way is easier to make the formyl cation. That's not the right way to draw it. So this is like an unstable intermediate. And then this, the benzene can attack, and then we can introduce a base in the end and finish up our reaction, and we can get benzaldehyde, which is benzene with an aldehyde. Oh, wait, I totally forgot to mention, it's different in one respect. So we have to use AlCl3, like in the Friedel-Crafts acylation, but we also have to use copper chloride. So this is copper 1 chloride. So those are just a few things you can add to benzene, and that's all for this video. Hopefully I'll make another one soon.